The rapidly reducing cost of wind and solar electricity generation highlights the need for low-cost, long-duration electrical storage that can transform intermittent renewable power into the predictable and dispatchable electricity generation and even baseload power. The cost of storage per unit of stored energy depends on the duration for which the system operates. This log-log plot of installed cost in units of dollars per kilowatt-hour versus the ratio of energy to power, represented in units of hours, compares the cost of different storage technologies. Today, pumped hydroelectric storage, or PHS, constitutes more than 99% of the deployed energy storage capacity worldwide. Most PHS installations are designed for 8 to 10 hours of storage, but with increasing storage duration, the installed cost drops. This is also true of underground compressed air energy storage, or CAES. Both technologies use zero-cost working fluids, namely water or air, to generate power through turbines that contribute to cost but do not store energy. With increasing storage duration, the installed cost drops and is lower than that of any other storage technology available today. However, both technologies require specialized geographies and have an environmental impact that limits their deployment. Lithium-ion batteries are a different story. The cost is relatively independent of the storage duration because their current design does not permit wide variations in the energy-to-power ratio, except at durations below about 1 hour. This is where high-power and high-energy lithium-ion batteries are differentiated. The cost band shown here represents projected future costs for lithium-ion and is between $150 and $300 per kilowatt-hour. Compared to pumped hydro and compressed air, lithium-ion uses costly energy-storing materials that set a floor on the system cost. Unlike enclosed batteries such as lithium-ion batteries, Redox flow batteries are structurally analogous to pumped hydro and compressed air by having independently scalable energy, namely chemicals and tanks, and independently scalable power, namely the power stack. The most well-developed battery of this type uses dissolved vanadium species and is called a Vanadium Redox Flow Battery, or VRFB. At long durations, its cost curve asymptotically approaches an energy cost that depends on the chemical cost of vanadium. This energy cost has varied widely, but even at the lower bound, is well above the cost of pumped hydro. Therefore, if a battery technology is to reach or beat the cost of pumped hydro without its locational constraints, it must have an exceptionally low energy cost. In the air-breathing Aqueous Sulfur flow battery, with sodium as the working ion, the storage cost becomes unprecedentedly low, below $2 per kilowatt-hour. If we use lithium instead, the chemical cost is still about $5 per kilowatt-hour. To arrive at the installed system cost, the cost of the storage tank, power stack, and miscellaneous cost are added to that of the chemicals. This green line here shows the installed cost if the power stack is very high, $4,000 per kilowatt. But with realistic systematic improvements such as decreasing the membrane resistance and cost, streamlining the cell designs, and using less or lower cost catalyst, the power cost can be decreased to levels where the overall cost at a given duration reaches that of pumped hydro and compressed air. Interestingly, such storage economics could be achieved for the air-breathing Aqueous Sulfur flow battery at an energy density 1,000 times that of pumped hydro, with minimal locational constraints. With further development, this new ultra-low-cost electrochemical storage option could enable the growth of intermittent renewable generation and decarbonization of the world's energy systems.